Everyone, let's solve some Leetcode today. So today we have Leetcode 410, that is split array largest sum. Now this problem is actually a hard problem, but I would call it crazy hard problem, because yes, there is an intuitive solution to it that you can actually code up, and it sometimes passes on the Leetcode. But the solution that we are going to discuss right now is something that is like the optimal solution, and that solution is very tricky to come up with. Coding that solution is not hard. Coding is very easy, but to be able to come up with that kind of solution is very non-intuitive for beginners, at least. The best I can say is that if you have solved a lot of problems like this, then you will be able to have the intuition to actually go ahead in that direction and discover that solution. So basically in this problem you will be having an integer array nums and you will have an integer k. Now we have to split the nums in k different subarrays. Remember that we are dealing with subarrays, not subsequences. So the elements needs to be contiguous, that is adjacent to each other. Now we need to divide this nums array in k subarrays in such a way that the largest sum of any subarray is actually the minimum sum possible. So what does this mean? Suppose that we have this particular array and now we have to divide it with two parts. Now what we can do is we can try to divide it in two parts like this. I can have 8 here. 8 will be another subarray, and this 7, 2, 5, 10 will be another subarray. 7, 2 and 5 and 10. So this is another subarray. We have two subarrays and the sum of this subarray is 8. The sum of this subarray is 24. So the largest sum is 24. Now we have to figure out, is there a way to divide this particular array in such a way that this largest sum will actually be less than 24, right? And yes, there is a way. So we can divide the array like this from here. Then we will have 7 to 5 here in one subarray, and we will have 10 and 8 in another subarray. So the sum here is 18 and the sum here is around 14. So as you can see that the maximum sum actually got reduced to 18, from 24 to 18. And if you try to actually divide it in any other way, then suppose that you want to divide it from here, this sum will actually become greater than 18, right? Yes, this sum will reduce, but it will become greater than 18. So the minimum sum that you can figure out is 18. So that will be the answer that you need to return. Remember, you are not supposed to return an array, because it is very clearly told to us that we have to return the minimized largest sum. So 18 is the minimized largest sum, and that's what we are returning here. And here we are only saying that a subarray is a contiguous part of the array. So it means that I cannot take a 7, then 10 and 8. 7, 10 and 8 is actually a subsequence. It is not a subarray, okay? Now yes, there is an intuitive way to solve this question. What you can have is you can have a recursive decision tree. So we will have a few choices. Why are we going to have a few choices? Well, first of all, we are going to create two subarrays right here, okay? We have to create two subarrays. So I can take this first of all in one subarray, and then the rest of the thing will be in another subarray, right? Subarray 2. Or I can do something like this. I can take these two in one subarray and the rest of them will be another subarray, right? Or I can do something like this. I can take these three in a one subarray and these two will be another subarray, right? Then I can simply take these 4 in one subarray and this 8 is going to be in another subarray, right? And then can I take this whole thing inside of a subarray and then let the other array be empty? No, I cannot do that. I need to have something in every array. Why? Because we are supposed to split. We are supposed to split this given array. So that's why this is not valid. We need to have something in every array. So it means till now it is valid. We can have this as one subarray, this as another subarray. So what we have is, we have a few decisions. So what will happen if I take 7 as first subarray? We have this, right? What will happen if I take 7 and 2 as a first subarray? And then what will happen if I take 7 to 5 as the first subarray? Then what will happen if I take 7 to 5 and 10 as a subarray? And here by taking 7 as the first subarray, all the other elements are going to be part of the other subarray, right? And here if I take 7 and 2 as first subarray, then all of these are going to be part of other subarray automatically. Yes, we will have to calculate their sum and everything, but that we can do easily in the code. But this is the intuitive way that you can actually solve this question. So you will have 7 here, then you will have a big subarray. You can divide this subarray in the other branches. You can have more branches everywhere, right? So you can divide it more. And yeah, that's kind of an intuitive way to do this. But this solution does not really pass on the Leetcode, because this solution will actually become a dynamic programming solution. You will have the I and you will have the K. So K is going to be the input parameter that you have to divide it into. So you will have to memorize this thing, or you can use true dynamic programming. But at the end of the day, you can have a time complexity like n square k, okay? And we are not going to go through this solution because it is an intuitive solution and it does not really pass on Leetcode. Yes, there are some optimization that you can make to make it pass, but we have a better solution. Actually, we have a much better solution, but that better solution is going to crack your head open. Now what we are going to do in this better solution is we are going to use binary search. It is a little bit non-intuitive, but it is definitely like the best way to solve this question. So how are we going to use binary search on this question? Well, we need to figure out what we were doing in the intuitive solution. What we were doing is that we were taking all the possible set of subarrays. So we had possible set of subarrays, right? We can have 7 as a single subarray, and we can have 2, 5, 10 and 8 as a subarray, right? Then we can have something like 7 and 2 as subarrays, right? And then we can have all the other elements like 5, 10, 8 as another subarray, right? We are dividing this in two subarrays because the k is 2. If k was 3, we would be trying to divide this in 3 subarrays, okay? Then we can have another subarray like this, 7, 2, 5, and then we can have 10 and 8 in another subarray, right? So this is another set of subarray, right? Then we can have something like 7, 2, 5 and 10. This is going to make one subarray, okay? And then we can have other subarray like 8, single 8. And now what we were doing is that we had a particular set of subarray, right? We had 7 and this one. What we will do is we will take the largest sum. So this will be the largest sum somehow, right? So it will come out to be like 25, right? The sum is going to be 25. Then once you have this sum, you can, yes, store it somewhere. So you will be having a minimum sum of 25 as the largest sum that you have figured out till now. Then you will go to the next subarray set. Okay, then you will calculate the largest sum here, and then it may be something else, right? And then you will go to next subarray, then you will go to next subarray, and you will keep on calculating the largest sum. And at the end of the day, after comparing all of these sets, okay, you will compare all of these sets and you will get an answer like 18. And this 18 is actually coming from this particular set, okay? So what is basically happening is that you are going through sets of subarrays. You have one set, two set, three set, four set, okay? You are going through all the 4 sets of subarrays and you are figuring out the maximum sum for all of those sets, and then you are actually just getting the answer by comparing all those maximum sums. You are returning the minimum sum that you can find. And this is the insight where you can actually use binary search. And this is where you need to think or understand that yes, we have multiple sets of subarrays, but not all of them are going to be answers, right? But we have to check each and every set. Why? Because we don't have a way to decide whether this particular set is going to be an answer or not. That is the only reason we are going through each and every set. Each and every set needs to be checked just to get the proper answer. So what it means is that if you try to go from subarray sets to sum, you will have to check each and every set of subarray, right? But what about the other way around? What if we try to go from sum to subarray? Now suppose that I take a random sum. The sum right now I'm taking is 20. Now I need to figure out, is there a way to split this entire array in such a way that the maximum or the largest sum for any subarray is going to be 20 or less than 20. Well, we can try to figure that out. So let us put a pointer I on 7. So we will have 7 here. So is 7 less than equal to 20? Well, yes, it is less than equal to 20. So we can make this subarray bigger, right? So I take more elements in the subarray. Now I will take 2. 7 plus 2 is what? 7 plus 2 is 9. Is 9 less than equal to 20? Yes, it is less than equal to 20. So I will go for another one. I will take 5. Okay. So 7 plus 2 plus 5 equals to 14. So is 14 less than equal to 20? Yes, I can take another element in this subarray. Now 14 plus 10. Now 14 plus 10 is 24. Okay. And 24 is not less than equal to 20. This is not true, right? What it means is that this particular subarray till 10 is not valid for this sum. The largest sum of this subarray is actually more than 20. But this subarray is valid, right? 7 to 5. The sum of the 7 to 5 was 14, which was less than equal to 20. So we will have one subarray like this, okay? Then we will take 10 in another subarray. So we will have another subarray and then we will have 10. So 10, is 10 less than equal to 20? Yes, it is. So we will again shift the I pointer to the next one and then we will add 8. Then is 18 less than equal to 20? Yes, it is less than equal to 20. So it means this is also valid. Now if I try to go any further, I don't have any elements, right? I don't have any more elements. What this means is that I can simply stop the loop and we have two subarrays like this. We have 7 to 5 and we have 10, 18. What this means is that we were able to split this array in two parts in such a way that the maximum sum or the largest sum of any of these two arrays is going to be less than or equal to 20. So what can we figure out from this? We know that we need to find out the minimum largest sum. We need to find out the minimum limit of the largest sum, right? So what we know is that since it is actually working for 20, we can try to go for lower numbers. I can go for 19. I can try to split this array into subarrays in such a way that the maximum sum will be less than or equal to 19. I can try to do that, right? Then in the same way, I can go to the 18, right? I can try to do that. If this also works, if there is actually a way to split this array in such a way that the maximum sum of any subarray is going to be 18 or less than 18, we can try to go for even lower values like 17 or 16, right? But where do we stop? That is the question. Where do we really stop? And the stopping point will have to be the largest element, not the sum, the largest element present in the array. Why? Because if we go any lower than 10, suppose I go to 9, then I will not be able to accommodate this 10 anyways, right? In any of the subarrays. But I need to be able to accommodate 10 also in one of the subarrays. So if I go to 9, if I go to 8, if I go to 7, I may be able to accommodate other elements, but I will not be able to accommodate 10 anywhere in any of the subarrays. So that's why 10 is going to be the cap. We cannot go any lower than 10. So we know what is going to be the minimum number that we need to check. But here we started with 20. And 20 was a random value that I took, right? How do I figure out what is going to be the maximum value or the largest value we can take and we can start from there? Well, we know that the k is equal to 2, right? Which means we need to divide this array into two subarrays. So what we can do is we can take the array and divide it into two parts. First is 7, the other one is this, right? Then I can divide it into this part, then I can divide it into this way, then I can divide it into this way, and then I just take the maximum that is present, the maximum largest number I could find out, and I can take that as the upper limit, okay? But this way is not really very good. At the end of the day, we just want to find out the upper limit. That upper limit does not have to be true, right? It just needs to be the upper limit, the place where we can start from. So the best way to do this is actually to just take all the elements and sum them up, okay? So if I take all the elements and sum them up, we will get 32. So 32 is the largest sum that we can get from this array, okay? So I can take 32 as the upper limit. So what this means is that the answer is going to be somewhere between 10 to 32, right? So we will have an answer between 10 to 32. And we know that for this particular array, the answer is going to be 18. So yes, 18 exists between 10 and 32. So we also have this way, right? I can take a sum and I can try to figure out if I can split this particular array into two subarrays such that the largest sum of any subarray is going to be less than or equal to 32. If it is less than or equal to 32, I can try to find out the lower numbers. I can try to check for lower numbers. If it is not less than equal to 32, I know that I need to go up. I need to figure out a bigger number. So here you can see that we have a condition and we can go either this side or this side. Right? Do you understand? I can check for lower numbers or I can check for upper numbers based on a condition here. And that's why we can use binary search. Remember that yes, we can go ahead from 32 till 10 and search for all of the values. Just figure these things out for all of the sum. But if we try to do this, we will end up going through each and every set of subarrays again, right? We don't want to do that. We don't want to go from 32 to 31 to 30 to 29 and all the way to 10 checking everything, right? Because it will not help us in any way. It will just make us go through the entire set of subarrays again and again and again. So what we need to do is we need to observe that, look, we are not supposed to check for each and every value, okay? We have a particular answer that we need to search, okay? We need to find out the minimum possible answer, right? So basically we have a set of these numbers and we need to search for a particular number based on a condition. So I can simply put binary search on it, right? Instead of going through every element or every number or every sum, I can just divide and then check for the condition and then simply eliminate half of the search space each time, right? And that will help us a lot and speed up our searching very quickly. So that is why we are going to use the binary search on the possible sum, right? The possible sum for this particular situation is just 10 to 32. Okay, for other array it can be different. All you have to do is just take the largest element from the array and then just take the sum of the entire array. That will give you the range in which you need to perform binary search. Now there is one more thing I want to clarify here. So here we have k is equals to 2, right? But what if it was not true? It was actually 3. And then here we were able to just take the two arrays. Okay, we were able to split in two arrays and the sum of each array was less than equal to 20. So will it be a problem if I just split it in two arrays, okay, and not three arrays? Well, no, it is not going to be a problem. Why? Because if we have the largest sum in any of these arrays less than 20, then we can simply take that largest array and break it in two parts, right? So I can have 5 and 10 and I can have 7 and 2 and the sum of these individual arrays is also going to be less than 20, right? So that's I don't have to exactly make 3 subarrays. If I can make 3 or less than 3 subarrays and make sure that for all of the subarrays this particular condition is true, largest sum of any of those subarrays is less than 20, I know that this particular number is fine. Okay, we can look for lower numbers, we can look for 19, 18 or some other number. But if I end up figuring out that no, I actually had to create more than 3 subarrays, I had to create 4 subarrays to actually make sure that the sum is going to be less than 20 for each and every subarray, then I know that I cannot have 20 as the answer. I need to increase the sum to reduce the subarrays. Okay, so then I will start checking for 21, 22, 23 or other numbers. So this is the condition that is going to help us figure out a binary search solution. So here is the binary search solution. We have the left pointer, we have the right pointer. Left pointer actually points to the largest element that is present in the nums array, and the right pointer is basically the sum of all the elements in the nums array. So we have a range in which we need to check for our solution. Now we will always calculate a mid in the loop. So we will have the mid and we will check if we can split the nums array in such a way that the largest sum of any of the subarrays is actually less than or equal to mid, that is this particular element. Then we know that we have found a possible solution. So we will set the result is equals to mid, and we will make sure that the right pointer is decremented to mid minus 1. Why? Because we need to find out the lower values now. Okay, so we need to find out the mid minus 1, mid minus 2, right? All those values. But if that is not the case, if we cannot split it in such a way, then we know that we have to find out a bigger value for the sum. So we will take the L pointer and we will shift it to mid plus 1. Simple as that. This is going to be the entire binary search solution. And this can split will actually be a method that will help us to figure out if we can actually split the array in such a way or not. And this can split is actually the easy part. It is nothing more than a simple greedy algorithm. You will see it in the code. So here is the code with all the proper comments. I will provide this in the description also. So first of all, we have the can split function. That is probably what you guys need to know, right? So in the can split function, we are taking a sum, okay, the largest sum that we are currently dealing with, and we will try to create subarrays. Since we always will be actually having at least one subarrays, we are going to start with subarrays needed with 1, okay, and the current sum is going to be 0 right now. Then we will take the nums, okay, each number in the num array, and then we will start checking things. So if the current number is actually greater than the largest sum, we know that it is bigger than the limit itself. So it is not possible to keep this number inside of any array, right? Because it is larger than the largest sum. So here we can directly return false that, okay, look, we cannot split this array in any way such that the maximum sum will be less than or equal to the largest sum. Then here we have the condition which is actually calculating the sum. Now if the current sum plus the current number is actually less than equal to the largest sum, we will simply update the current sum, okay, and then we will move on to the top of the loop again and we will go for another number. But if it is not less than the largest sum, okay, if the current sum plus number is not less than the largest sum, it means we need to create another subarray to actually accommodate the number. So in the else block, we will simply increase the number of subarrays that we need, and then we will take the current sum and we will set it to num. Why are we setting it to num, not 0? Well, that is because we need to take the current number into the next subarray, right? And the next subarray is going to start with the current number, not the first element. So suppose that we have an array like this and we were able to sum everything till this point, okay? So we have a subarray of this one, and I'm trying to add 10 into the sum of the subarrays so that I can take 10 also inside of this current subarray. But the situation is that the current sum of this subarray, that is 14, plus the next number 10, is actually greater than the largest number, right? So it is greater than the largest sum. And the largest sum, suppose it is like, just say, I don't know, like 14 itself. I'm supposing that it is going to be 14, okay? So if this is actually larger than the largest sum possible or allowed, then we know that we cannot add 10 inside of this subarray anymore, right? So it means I need to create another subarray. So the another subarray will be starting from here, okay? And that's why I'm taking the current sum variable and actually setting it to n or num basically, because 10 will be the current num. So it is going to start with the 10. The first value itself will be 10, and then we can just keep on increasing and just add 8 in the next iteration and so on. And once we have gone through the entire for loop, we will know how many subarrays we need to actually make sure that the sum of each subarray is actually less than or equal to the largest sum. And then we will check if the subarrays needed is actually less than equal to k. Okay, so k is the allowed number of subarrays that we can make, and the subarrays needed is actually the proper number of subarrays that we need. So if the subarrays needed is less than or equal to k, that means it's fine. We can simply return true. Okay. Otherwise, if we need more than k subarrays, we can simply return false. So we will get true or false from this condition. And now here we are going to start our binary search. So we have the left and right pointer, and then we have res is equals to right. So we are going to make sure that we are taking the worst case as the answer. So we will take result is equals to right. Okay, that is sum of all the elements. And then we have the while loop. So while left is less than equal to right, we will figure out the middle element. So this particular expression will help you figure out the middle element. This expression makes sure that you do not actually deal with any overflow condition. So try to use this expression whenever you are trying to find out mid. And then here we are using the can split method on the mid. Now if the result is going to be true, then we will go for this. We will set the result to mid, and then we will set the right to mid -1. Otherwise, we will set the left to mid +1, just like we discussed earlier. And once this entire loop is done, we will get the result. We will simply return the result, and that will be the answer. So now let us run it and see what happens. So yeah, our solution runs in 4 milliseconds and beats 31.76% solutions on Leetcode. We are passing all the 34 test cases. It's a pretty efficient solution. Now let us discuss the time and space complexity for this particular solution. The time complexity is order of log of s multiplied by n. S simply means the sum of all the elements. So suppose that you have an array like this. You have 1, 1, 1, okay, 1 and 1. So here every element is just 1, okay, right? So the minimum number or the minimum sum you can have is 1, right? Because each and every element is just 1. So the maximum out of each and every element is also going to be 1. And then the largest element or the upper limit of solution that you need to check for is going to be sum of all these elements, that is going to be 5, right? So as you can see that the range between the left pointer and the right pointer is what? It is 5, right? The range is simply 5. And since we are going to run the binary search on this range, we will actually end up going for log of this range. So the range is basically what? In the worst case scenario, range is basically sum of all the elements. That's why the r will be replaced by s. So log is log of s. So time complexity will be log of s. That's why we have this log of s here. And then we are multiplying this with n. The reason we are doing it is because inside of this binary search loop or while loop, we have another function can split, okay? And this function runs in order of n time complexity because we will have to go through each and every element of the array in this can split function. So that's why this function will be run each time the while loop is running, and that's why we have multiplication sign here. So you can also write it something like n log s. It looks more better, I would say, but this expression actually shows what is really happening. We have a binary search, and inside of this binary search we are running an order of n function. So this represents the workflow a little better, but at the end of the day you can also write it like this: n log s. The space complexity is going to be order of 1 because we are using binary search and we are just using a few variables in the can split. We are not actually allocating new space for hash maps or for arrays or any other thing. So that's why the variables that we are using or we are allocating in binary search and in the can split function are going to take the same amount of space no matter what is the size of the nums array. So the memory that we are using in the functions does not depend on the size of the array, right? Does not depend on the input size. And that means the memory consumption is going to be fixed for all the functions, and that's why we are saying that it is going to be constant space complexity. So yeah, like the video, subscribe the channel. If you have some kind of question that you would like me to target, or you have some kind of topic that you would like me to talk about, just let me know in the comments. Now we will meet in the next video. Till then, bye.